So I downloaded the file 6.1 review from Canvas. On the first page, we have important differentiation rules. The first one is power rule. The derivative of x to the n is n times x to n minus 1. The second one is constant multiple rule. It says if c is a constant, is a number, and you multiply it by a differentiable function, the derivative of that constant times f is equivalent, saying that, hey, let us take the derivative of the function and multiply it by constant c. Addition and subtraction rules. The derivative of the sum of two functions is equal to the sum of their derivatives. The derivative of the difference of two functions is equivalent to taking the difference between their derivatives. Product and quotient rules. If you have the product of two functions, the derivative is equal to f prime g plus f g prime. Or you can write it this way: f times g prime plus f prime times g. The order is not important. The second one, our famous quotient rule. If you have f divided by g and you're taking the derivative, it's equivalent saying that it's the derivative of f times g minus f times the derivative of g divided by g squared. So we copy down the denominator and raise it to 2. Two important limits. The first one is the limit of sine theta over theta while theta is getting closer and closer to 0. If we plug in 0 here, the outcome is 0 divided by 0. So we can use L'Hopital's rule, which says, hey, this limit is equivalent, saying that you have the limit of the derivative of sine over the derivative of theta as a variable while theta is getting closer and closer to 0. You know that the derivative of sine is cosine theta, and the derivative of theta as a variable is just 1. And note that you're taking the limit while theta is going to 0. So since cosine theta is a nice continuous function, we plug in 0. We have cosine of 0, which we know is equal to 1. That's why the limit of sine theta over theta while theta goes to 0 is always 1. The same for limit of cosine theta minus 1 divided by theta. This limit is also exists and it is 0. So if you plug in 0 on the numerator, you have 1 minus 1 divided by 0 or 0 over 0. By applying L'Hopital's rule, you have the limit of the derivative of cosine theta minus 1 divided by the derivative of theta while theta is going to 0. On the numerator, you have negative sine theta divided by 1. Theta goes to 0. Again, sine is a nice function, so we can plug in 0. We get negative sine of 0, which is 0. So power rule combined with the chain rule. Suppose n is any real number and u is a function of x. And suppose u is differentiable. The derivative of u to the n is n u to n minus 1 times the derivative of u. So n u to n minus 1 times u prime. In general, if you have a function like g and it is raised to exponent n, you can take the derivative. And it's the same as saying that, hey, I have n times the function raised to n minus 1 times its derivative, applying the chain rule. Some important inverse trig functions. The derivative of inverse sine with variable x is equal to 1 divided by square root of 1 minus x squared. The derivative of the inverse of cosine is minus 1 divided by square root of 1 minus x squared. The derivative of inverse tangent is equal to 1 over 1 plus x squared. When you have inverse of cosecant, it is negative 1 divided by x times square root of x squared minus 1. The derivative of inverse secant is 1 divided by x times square root of x squared minus 1. And finally, the derivative of inverse of cotangent is negative 1 divided by 1 plus x squared. Let us continue to next derivatives. The derivative of ln of u is u prime over u. So u prime over u. If you have ln of g of x and g of x is any function, the derivative of ln is equal to g prime over g. Two important limits. Limit of 1 plus x raised to 1 over x while x goes to 0 is equal to e. So if I switch x and use 1 over n, n goes to infinity, and you have the limit of 1 plus 1 over n to the n, while n goes to infinity, which is equal to e. That's how we define Napier number. And for hyperbolic functions, the inverse of sine hyperbolic function is equal to, take the derivative, 1 over square root of 1 plus x squared. The inverse of cosine hyperbolic, the derivative is equal to 1 over square root of x squared minus 1. When you have the inverse of tangent, it's a hyperbolic function, the derivative is 1 over 1 minus x squared. The derivative of inverse cosecant hyperbolic is equal to negative 1 over absolute value of x times square root of x squared plus 1. The derivative of inverse of secant hyperbolic is equal to negative 1 divided by x times square root of 1 minus x squared. And finally, when you have the inverse of cotangent hyperbolic, the derivative is equal to 1 over 1 minus x squared. Very well. Now let us talk about fundamental theorem of calculus and go over some integrations. Fundamental theorem of calculus says, suppose you have a nice continuous function on a closed interval a to b. If the integral of f of x f of t dt, while t ranges between a to x is equal to g of x, then you can take the derivative of both sides and the derivative of integral. Intuitively, they are opposite of each other, and you can cancel out the integral by taking its derivative, and it's equal to f of x. The second one, if you have f as an antiderivative of function f, lowercase f, the meaning of that, if you take the derivative of function f, it's equal to lowercase f, then the integral of f of x, while x ranges between a to b, is equal to f of b minus f of a. Very well. Some integrals, indefinite integrals. The integral of a constant c times f is equivalent, saying that, hey, let's take the integral of the function and multiply it by constant c. The integral of a constant like k is equal to k times variable x. When you're taking the integral with respect to variable x is kx plus the constant of integration, c. When you're taking the integral of the sum of two functions is equivalent, saying that, hey, let's take the integral of each of them separately and add the outcomes. The integral of x to the n dx, note that n is not equal to -1. It means that we're not working with the integral of 1 over x. It's not this case. Is the same as saying that, hey, that integral is equal to x to n plus 1 over n plus 1 plus constant of integration. You can always check these integrals by taking the derivative of both sides. The integral of 1 over x dx is ln of absolute value of x plus constant of integration. The integral of e to dx is equal to e to dx plus c. The integral of a to dx is a to dx divided by ln of a plus constant of integration. The integral of sine is negative cosine. The integral of cosine is sine. The integral of secant squared is tangent plus constant of integration. The integral of cosecant squared is negative cotangent plus constant of integration. Wherever you see the integral of secant tangent, this is equal to secant. The integral of cosecant cotangent is minus cosecant. The integral of 1 over 1 plus x squared is inverse tangent plus c. The integral of 1 over square root of 1 minus x squared dx is inverse sine. The integral of sine hyperbolic is cosine hyperbolic, and the integral of cosine hyperbolic is sine hyperbolic. Very well, let us move on. One of the important rules in taking the integral is substitution rule. So suppose u is equal to g of x and it's a differentiable function. And suppose it's defined on an interval like I, and function f is also continuous on I. And note that this I is the range of your function, because you're working with the composition of two functions, function f composed with function g. The integral of f composed with g times the derivative of g is equal to the integral of f of u d of u. So we can simplify an integral by using substitution. The integral of tangent is equal to ln of secant. Let's see, what else do we have? Okay, so the substitution rule for definite integrals. Suppose the derivative of function g is continuous on a closed interval like a and b, and f is also continuous in the range of function g. Again, since we are composing these two functions, the domain of one of them is the range of the other one. Then the integral of f of g times g prime when x ranges between a and b is equal to the integral of f of u du while u ranges between ga and gb. Very well. Integrals of symmetric functions. Suppose function f is continuous between negative a and a, you have a closed interval. If your function is even, like cosine is an example of an even function, then the integral of f of x from negative a to a is equal to 2 times the integral of the same function of 0 to a. So think about cosine. Cosine function, negative pi over 2 and pi over 2. So because of symmetry, these two sections have the exact same area. So instead of taking the integral between negative pi over 2 to pi over 2, you just say, hey, let us just find the integral of the function between 0 to pi over 2 and multiply it by 2. If you have an odd function, then the integral between negative a to a is equal to 0.